Okay, so last time, right, you guys started looking at the dot product of vectors and groups together. Let me share screen. So we have these definitions, right? We have this algebraic definition where you just take the common components, multiply them, and add. And then we have this geometric definition that you can also take the length of one vector times the length of the other vector times the angle between them. So that's kind of neat, right? And it's not obvious at all that these are the same definition, like I've said, but I think that, like I said, there's an argument on the very last page of this handout. And you started computing and stuff. And I just wanted to look at these last couple, maybe these last couple, and just talk a little bit qualitatively about what the dot product is telling you. And then we can talk about the cross product a little bit. And it's kind of weird, but then we can sort of go into group work and work on that. So, all right, so, oops, yeah, okay, cool. Anything else I need to address? Any logistical annoyances or anything? We're all good. Okay, yeah, so the dot product, right? So it says, right, so we've got this, I'm just gonna talk mainly about the geometric interpretation today. So the length of V times the length of W times the cosine of the angle between, right? Theta is angle between V and W. I guess what I'm saying is if this is V and this is W, and this is theta right there. Now, a couple things. I think problem 9, I'm not sure if all the groups got to it, but problem 9 on that handout is showing that you could actually find the the angle between two vectors in space now, which is kind of cool because I could have like a vector pointing this way, vector pointing this way. I feel like before you knew what the dot product geometrically, it would be pretty hard to figure out the exact angle. Like you might have to figure out the exact plane and try to move everything in that plane into like a two-dimensional thing, and then I don't know. Could be I could see that being quite difficult. But this kind of gives you just an automatic way to do it. You just, you know, you could solve this for theta. You could say theta is the inverse cosine of V dot W over length of V times length of W, right? And then solve. So you basically compute this and then have your calculator tell you what angle that is. Make sense? Now, yeah, so I was going to say, okay, well, let's just think, but I want to think qualitatively about what does like the dot product mean, quote unquote mean, because I think some people are asking me that, like, what does the dot product mean? And I think there's a couple different possibilities here. And that's not totally satisfying. But one thing we saw here was like, notice this number 11 on here, which is basically V and W are perpendicular if and only if their dot product is 0, right? So the sign, you know, maybe it's a little bit hard to say because it depends on the magnitude of each, because this in this interpretation depends on the magnitude of each vector. But at least you can at least think about what the sign of the dot product says. But the sort of the sign, IGN of the dot product has a nice meaning. And let's just think about it. Cosine, since we know we know magnitudes are both positive numbers, or non-negative numbers. Cosine, so it really the sign of the dot product depends on the sign of the SIG of cosine. Right, and so, for example, if theta is 90, is pi over 2, 90 degrees, cosine theta is 0. So if IE, but think about this, if the angle is 90, that means they're perpendicular to each other, the two vectors. So i.e., if V is perpendicular to W, then the dot product is 0. And vice versa, like if the dot product is 0, then this meant cosine theta was 0, right? So that's a big thing. Like just so that's the, I mean, the sign being no sign at all, 0, it tells you something about, you know, this is an important fact we're going to use over and over again. So you just want to start to get used to it. Like anytime you're asked about whether two vectors are perpendicular, you immediately just want to try to compute the dot product of those vectors and see if you get 0, right? That's already a nice thing. And then in general, but also like if, so let's think about the sign, what cosine is, how cosine works, right? Cosine is the x coordinate of a point on the unit circle, right? That's sort of the right definition. So if I draw the unit circle and I have a point here at angle theta, then remember the coordinates of this point are cosine theta, sine theta. That's kind of the whole point of cosine and sine, especially if you want to extend past 90 degrees, like what they mean, right? So, and that's how you can see that cosine of 0 is 1, and cosine of 90 degrees is 0, cosine of 180 degrees or pi is -1. If you keep this picture in mind, it's easier to see, you know, remember all these things. So right, so let's see. So then cosine of theta is greater than 0 for 0 less than or equal to theta less than pi over 2, right? Cosine theta equals 0 for theta equals pi over 2. That's what we were saying just right there. And cosine theta is negative for theta for pi over 2 less than theta less than or equal to pi. I guess I'm just using these angles 0 to pi because if we take the angle between two vectors, it's at most 180, like 180 is the biggest angle you could have between two vectors. So right, because if I'm over here now, all of a sudden the cosine is the x coordinate's negative. So what that says then, since v dot w, the sine of v dot w equals the sine of cosine, sine, not sine, but gn. So if v dot w is sort of positive, if and only if v and w make an acute angle. So you can say something vague like, okay, if I actually take the dot product and I get a positive number, that means they vaguely point in the same direction. Not like the exact same direction, but at least they're sort of like, they're not pointing in opposite directions. You know what I mean? Whereas if v dot w, and I guess I can just say the same thing here. I'm just repeating this just to get all the cases. If and only if v is perpendicular to w, so that's the dot product is 0, and it's negative if and only if v and w make an obtuse angle. Remember, obtuse is just like. So I have some vague sense. I mean, sometimes you want to just like get some vague sense. Do these vectors point in vaguely the same direction or vaguely the opposite direction. One way to do that is to just take the dot product and see. Good. We will talk about projections at some point, in which case there's another way to interpret the dot product of two vectors as sort of the projection of one onto another, but we'll talk about that in a little bit. And then I guess it's also worth noting just what I said here, like basically if the angle between the two vectors is 0, if it's v dot v, you basically get the magnitude squared, right? Like up in that formula at the top there, if v and w are the same vector, then v dot so maybe I'll just say like special case. V equals w, then v dot v equals magnitude of v times the magnitude of v, right, times cosine of 0. So that's just the magnitude squared. So if you dot a vector with itself, you get its magnitude squared. Make sense? Like this is all unobjectionable or something? You guys are just like, cool, whatever. Okay. Yeah. All right. Like I said, I'll give you some homework on the dot product. But then, yeah, I don't think there's much more to say. Except when we come back to projections. Oh, I guess one thing I keep meaning to say, and keep thinking of saying, and keep forgetting to say is, I'm trying to be careful here and make this dot kind of big. And then there's a little dot right there because that's just multiplication. Because magnitude of v is a number, right? Up there too, I have little tiny dots between magnitude of v, magnitude of w, and between magnitude of w and cosine theta, because that's just multiplication of numbers. But then, so when you're writing stuff, it's good to like draw kind of a big thick dot as like your dot product. And to remember that the dot product gives you a number, not a vector, right? That's another important thing. There's just things to remember, like dot product is a number. Okay. Then we have the cross product, which is also very important, but it's definitely a weirdo. Compared to dot product, at least is something you could sort of see doing. At least the algebraic definition, like multiply the x components, multiply the y components, multiply the z components, and add. It's a way to get a number of two vectors. This is weird. This is like, I want to take two vectors and make another vector. And again, the book gives two definitions, like an algebraic definition and geometric definition. And the algebraic definition is very strange when you first look at it. You see this like, so the components of V are V1, V2, V3, the components of W are W1, W2, W3, and then you get this weird formula. And there's some structure in this formula, and we'll talk about it. Like you might notice the I component doesn't contain V1 or W1, it only contains the 2s and the 3s, like the J and K components of the initial vectors, you know? And the same thing, the J component doesn't contain the J components of it doesn't contain the V2, W2. Yeah, does that? And there's some sort of pattern. There's like a 2, 3 minus 3, 2, 3, 1 minus 1, 3, 1, 2 minus 2, 1. There's some sort of pattern, right? I mean, it's something, there's a reason it's chosen to be this way. And you just have to look at it enough times. There's a quote that like you never actually learn new mathematics, you just get used to it. So you see this formula looks so strange. Then if you just look at it over and over again and practice computing some cross products and stuff, then eventually you're just like, all right, I guess that's a formula. I guess I'm used to it now. And then the geometric definition is even a little bit stranger. I actually think the direction is more important here. So the idea is to create a vector perpendicular to two given vectors. So I should say that cross product really only works in 3D. There's not really like a 2D cross product exactly, or like even, well, I mean, there are ways to talk about like 4D and 5D cross products and stuff, but this is really a 3D thing, because if I have two vectors pointing in two different directions, I want to somehow create a vector perpendicular to both of them. That seems like something you could plausibly want to do. Maybe, I don't know. I mean, we'll see lots of good reasons why very soon, but right, I'm gonna just create a vector perpendicular to both V and W. And then it's weird, the magnitude is given by the area of the parallelogram formed by V and W. So if V and W are sitting here in space, then you can imagine, like, think about the adding the two vectors, right? So if you add V and W, you get to this corner. And so you can think of there being a parallelogram made by these two vectors. And it turns out, surprisingly, that this formula will give you the length of this vector, this resulting vector, will be the area of this parallelogram. And the direction I said perpendicular, and there's a right-hand rule. Did we talk about right-hand rule already this semester? Why do I feel like I talked about the right-hand rule recently? What was I just talking about the right-hand rule? Yeah, so what's the right-hand rule? So let me share so I can. So right-hand rule is something like this. You have two vectors, right? You point your fingers along the direction of the first vector, V. And then you curl wherever W is, you sort of curl your fingers. Like if V was this way and W was straight up, I would turn my palm and then curl them towards the other vector. All right, if V was down, I would curl them down. And then you stick your thumb out and you see which way your thumb points. Because like there's two perpendicular, right? There's two perpendicular directions in these two vectors. It could be that way or it could be that way. Straight up or straight down. And so, yeah, the idea is you stick your fingers out in the direction of V, curl towards W, whichever way, however you have to turn your hand to curl towards W, stick your thumb out, and that's the direction of the cross product. It comes up in physics all the time. It's a right-hand rule. I always thought I had an advantage as a lefty, because if I'm working on a test or something, I can still do the right-hand rule without putting my pencil down. Yeah, lefties win always. Very proud lefty. Come at me if you disagree. Yeah, so there's a thing called right-hand rule you have to get used to. And I said these are both very strange definitions, and they're both, again, not clear at all that they would have anything to do with each other. So at some point, basically what I'm gonna ask you to do in group work, I might talk about this formula a little more just to sort of look at some of the structures of it, but basically we're gonna go into group work and just practice. So you're just gonna like practice computing these two guys. And so if you compute V cross U, oh, I actually say it, I was gonna say, what do you do? I was gonna ask you, what do you do to check it's perpendicular to the original vectors? Well, you just dot it. Once you compute this, you dot it with V, see you get 0, dot it with U, see that you get 0. Yeah, there's also things here. This might be one of the first things you see in mathematics that's not commutative, that the order matters. You think about that you can check that algebraically, but you can also check it. You can also think it mattered which one I said was first in terms of the right-hand rule, right? If I stick my fingers in the direction of V, curl towards W, that's different than sticking my fingers in the direction of W and curling towards V. You can actually see that those are opposites of each other. So it's kind of weird. You actually get something that's not commutative, where if you switch the order, you actually pick up a minus sign. So there's all sorts of some weird stuff. So I'm going to have you guys do that. And yeah, this is sort of some of the same things we were checking about the dot product. And then, oh yeah, then some general stuff, right? And then, yeah. Actually, maybe I should just, well, there's this last thing, like if you know about determinants, find a nicer way to write the algebraic formula. Maybe I'll go ahead and talk about that just a little bit before we break up into groups. So let's write out this cross product definition. You just have to sort of write it out a few times. I'm actually going to write it maybe slightly differently than I have it on there. I'm going to throw in an extra minus sign at one point. I'm not sharing the screen, am I? Okay. Let's just, we got to practice writing this thing out. So cross product. So let's say, right, V is V1I plus V2J plus V3K, right? W is W1I, W2J, W3K. Then V cross W, the algebraic definition, and it's there up on the screen, but you can check. I'm going to take these four numbers, right? It doesn't involve these two numbers. It just involves these four numbers. And in fact, you might be able to see sort of a pattern, V2W3 minus V3W2. So there's sort of like diagonal pattern. You guys see that if I'm pointing at the board, like V2W3 minus V3W2. I. So that's what the I component is. I'm going to actually throw an extra minus sign in the J component. And then, so I'm going to forget this, cover this up, but then it's like, if I cover this up and then use a minus sign here, it's actually V1W3 minus V3W1. So again, it's that sort of diagonal pattern. Can you guys see that? I think I did that right. Because if I distribute the minus sign, this becomes plus, which is what the formula is on the page. And then now for the third one, I'm not going to look at these, and I'm going to do that same diagonal, V1W2 minus V2W1, right? Well, it's minus because it's the formula. And it turns out to be the right formula to make a vector perpendicular to the two given vectors. But I'm just saying if I want to look at this diagonal pattern that I was talking about, then you have to put a minus here to make that continue to work, sort of. Like, so I'm getting at, like this one, I'm sort of covering up the D's and just doing this diagonal pattern for this. For the middle one, I'm covering up these and doing the diagonal pattern. But it turns out it needs a minus sign. And then for the K component, I'm covering up these and doing the diagonal pattern like that. And that's the thing I was going to say. If you've ever heard of the determinant of a 2x2 matrix, I mean, you'll learn more. You might have seen it, but you don't have to have seen it. But and it'll definitely, if you take linear algebra, you'll learn a lot about it. But if you have just like a matrix is just an array of numbers. And if you have a 2x2 determinant array, a matrix, the determinant is, well, it's written this way with like absolute value signs. Like I use square brackets for a matrix, or some books use parentheses. And it's defined to be AD minus BC. And it turns out it's like, has all these important properties. But you see it's the same pattern, the same AD minus BC, the same pattern I was doing up there. So in fact, so if you see this before, great. If not, it doesn't matter. It's just something called the determinant that turns out to be important. And it actually does help, once you really understand it, explain where this formula comes from. But if you do that, you can rewrite this as, notice I can rewrite this way as right? If you think about this expression right here, if I rewrite it as a determinant, I think that gives you the same thing. Is that right? V2W3 minus V3W2, yeah. And then that's in front of I. Remember, this is a vector. So that's I. And then minus V1, V3, W1, W3, J plus V1, V2, W1, W2, K. And so that ends up being, so you can sort of like, once you recognize 2 by 2 determinants, you can sort of rewrite this way and it looks a little bit nicer. You know, again, this doesn't include the I components of V1, V and W. This doesn't include the J components of V and W. This does not include the K components of V and W. Like there's just ways to try to remember how this all works, right? Makes some sense. I'll say there's actually something called the 3 by 3 determinant. And you actually package this all together into what's called a 3 by 3 determinant, which I might as well write down. Because that's the way some people, I mean, it's gonna look kind of silly because I'm basically gonna just say the 3 by 3 determinant looks something like this, and then say, well, then we can actually write, you know, you can actually write the cross product down. But it turns out it's sort of important, like that it's sort of, the determinant actually tells you things about areas and volumes. And like I said, the magnitude of the cross product is supposed to be the area of a parallelogram. So there's a relationship. So there's something called the determinant of a 3 by 3 matrix. So now I just have A, B, C, D, E, F, G, H, C, I, J, K. I want to using, so let's just use M. And it turns out that the formula for this is in terms of 2 by 2 matrix and 2 by 2 determinants. What you do, so let me write it this way. Again, it's more like an absolute, we write like an absolute value sign. I don't know, I can put an I there and we're sophisticated enough to know it's not the I vector I, yeah, maybe. I just feel like it's gonna mess me up. Just using alphabetical order. It turns out that here's what it is. So I'm gonna write this down and then try to explain where what the pattern is that I'm doing. Or maybe you guys can see it. So where these are the 2 by 2 determinants. Again, not at all clear what this is random and goofy. It turns out it's important. What am I doing here? There's an A, there's a B, there's a C. That's the first row of this, right? What am I multiplying A by? Well, if I still have that skill anymore. If you look at it this way, if I isolate this A, then the 2 by 2 that's left over here is what I'm taking the determinant of. Right? Or another way to think about this is if I look at A and then delete the row and column containing A, what I'm left with is the proper 2 by 2 determinant. And then there's this minus sign, which is there for reasons. If I take the B and then delete the row and column containing B, I get DFGI, which is exactly that. And then I do plus C, and I cover up the row and column containing C, I get exactly the other, the DEGH. Okay, this is all just like random nonsense at this point, but there are patterns. And if you think about this, well, I could move, I mean, it starts to look a lot like that, especially if I move the A, the B, and the C at the end instead of at the beginning, right? I put the A, the B, and the C here. It starts to look a lot like that. And in fact, so I want the A to be like I, the B to be J, the C to be K. So in fact, V cross W, there's this really compact way to write it, which is I put the I, J, and K along the top here, which is already a little strange to put vectors inside matrices, but whatever, it's just a formal nonsense. And then notice, this is like EF corresponds to V2 and V3, D corresponds to V1, so really this is V1, V2, V3. And this is W1, W2, W3. So in fact, there is a nice way to package the entire weird formula into this 3×3 determinant. Really, you're just sticking the weirdness in the determinant formula instead of, you can't really get rid of the weirdness, but it's inside the determinant formula. So some people, if you've seen 2×2, 3×3 determinants, you can think about it this way. But honestly, it's a formula that you have to sort of get used to. Does that make sense how I sort of packaged all this together? Like if you write out what the 3×3 determinant means, you do this times this determinant right here, minus this J times that determinant, plus K times that determinant, and that's exactly what you get. And if you write out those 2×2 determinants, you get that weird formula we started with. Fair? Okay, so like I said, like we did with the dot product, I want you to just start to play with this a little bit, get used to it. Just compute out just directly using the formula. At some point, I guess it's not until 14 or 15, you want to start using the geometric definition. The first few problems just use the algebraic definition we've just been talking about. Okay. So can we go back to the same groups that we were in on Monday? Does that sound good? If you weren't here for some reason, then you can just join a group. But yeah, we've only got 20 minutes left, so let's jump into groups. Start doing number 13. Again, you might want to pull this up on your device so you can see this formula. I guess the formulas are up on the board too. But let's do that, and I will pause the recording. Second here. Okay, let me just